My name is Tess SANDBROOK. I'm a senior undergraduate at Worcester Polytechnic Institute, and I'm working alongside Jeff Smith at Sandia National Laboratories to perform explicit analyses of shear band formation in impacted pressure vessels. Shear bands are localized areas of very high strain that form in situations of high impacts and can occur within microseconds. In the figure, you can see them represented as large, red areas crisscrossing the model. They can lead to plastic deformation and severe material failure, and so it can be important to design products in such a way that shear bands don't form in the first place. My research is studying how macroscopic shear bands form in pressure vessels that contain potentially high-risk materials, such as those used as heat and electrical sources in spacecraft missions. The pressure vessel for the Mars Science Laboratory, also known as the radioisotope power system, can be seen in the bottom figure. In the event of a crash, the radioisotope contained within these vessels could leak out of cracks that form due to shear bands. Because of the safety hazards posed by physical testing, as well as these significant costs, my research will use finite element analysis, a computer-based numerical simulation in Abacus, to gather data. Ultimately, my two main goals are to identify the best way to model shear bands, specifically in geometry similar to the radioisotope power system, and to reduce the effects of those shear bands by varying internal radius sizes. Because the geometry of most pressure vessels is very complex, using a simplified model to determine where and how the shear bands form can improve the runtime of the simulation, while still providing valuable information. The simplified geometry I used is a 1 by 1 inch cylinder with a rectangular hole in its side. The vessel is restricted from moving or rotating except in the vertical direction, and is given a downward velocity of 200 meters per second, causing it to impact the pinned plate below. At Sandia, this geometry is being considered for physical testing due to its ability to be easily machined. This could lead to a future comparison between those physical tests and a finite element analysis. For my project, 3 different materials were applied, one at a time, to the vessel: OFHC copper, tantalum 10 tungsten, and steel 316L. Currently, there are varying views and opinions on the best way to use finite element analysis to study areas of high strain. Due to a shear band's short time frame of initiation and large impacts, numerical analyses can vary widely in terms of accuracy. 2 different numerical methods can be used to model shear bands: implicit and explicit. Originally, I had wanted to run both an explicit and implicit fully coupled solution and compare the results. However, only an explicit analysis was performed due to time constraints and computational limitations associated with contact and element distortion. Within this explicit analysis, I used the Johnson-Cook model with both rate and temperature dependence to define the parameters for the simulation. This produced output variables such as stress, equivalent plastic strain or PEEQ, and nodal temperatures. These outputs helped identify where shear bands formed. For example, the 3 figures on the left show a map of the strain on the model with different mesh sizes. The green areas indicate higher strain values than the blue areas, leading to the conclusion that shear bands could develop here in a more realistic model. Because there so far has been no physical testing for the geometry I used, I wanted to ensure that the data I was collecting from the analysis was correct. To do this, I ran a similar analysis on a short rod. While the boundary conditions were changed, the Johnson-Cook and material parameters stayed the same. The results from this test compared favorably to testing and analysis performed at Sandia. With this information, I was confident that the input data used to define the analysis was correct and the results were accurate. However, even though I was confident in the outputs of the simulation, there were some limitations in how they could be used. The maximum strain was found on the bottom surface of the pressure vessel due to its impact with the plate. This skewed the color map away from areas of interest, making it hard to judge the precise location and severity of potential shear bands. To attempt to solve this, I restricted the range of strain values, allowing a clear presentation of the lower 2 corners of interest. Here, the red areas are highest in strain, followed by yellow, green, and blue. Another limitation was the size of the mesh that could be used. A finer mesh could lead to more precise results, and indicate an even greater disparity in strain in the 2 lower corners. However, finer meshes take more time to run, and in this model also led to severe element distortion. Now that I had determined the locations of high strain in the simplified model, I applied the same setup to a more realistic pressure vessel model that was completely enclosed. I found that the strain results and locations were similar to the results found in the previous simplified geometry. Once this was confirmed, I began varying the internal radius size with the goal of reducing the maximum strain in the lower two corners. The two radius sizes that I chose, 1.69 and 2.4, were based on predefined internal volume limitations associated with the model. To compare the strain levels reached with each radius size, I plotted the strain in two elements over time, one on the left lower corner and one on the right. Here, you can see the deformation and color map for both radius sizes using OFHC copper. The red highlighted elements are those selected to plot the strain in the shear band region. In these plots, the red line represents the element on the right, and the blue line represents the element on the left. While there are small differences between the graphs of the 1.69 radius and the 2.4 radius, there was not a significant change in the maximum strain level reached. There was also not a significant difference between these two graphs and a strain plot of the model with no radius. Next, I tested the tantalum 10 tungsten. Again, the red highlighted elements were used to plot the strain in the region. With this material, the strain on both the right and the left side was reduced as the radius increased. Finally, I tested the geometry with steel 316L. With this material, the right corner did exhibit a decrease in strain value with an increase in radius size. However, the left side strain value actually increased slightly. This could be due to the material characteristics and the relative deformation in the model. There was also almost no difference between strain values of the model with no radius compared to the model with a 1.69 radius. While analyzing the strain in the model for different materials is important, the properties of each material cannot be overlooked, as they may not all be suitable for every design. The contents of the pressure vessel must be taken into consideration, and if there are any potential reactions between the contents and the material of the vessel. Also, in regards to the radioisotope system of the Mars Science Laboratory, it is helpful to choose a material that exhibits high strength when exposed to high temperatures. The materials used in this project each have certain advantages that may be useful in a variety of situations, and so it was beneficial to study their reaction to a high impact. However, deciding which material is best suited for the job will require much more testing. Some of this testing may include using smooth particle hydrodynamics, or SPH, to model the internal contents of the pressure vessel. This would help in modeling fluid and how that could potentially affect the deformation of the pressure vessel. Testing performed at Sandia indicates that including internal fluids while modeling shear bands in pressure vessels has a significant impact. Also, running a coupled implicit analysis could yield different results from the explicit analysis, particularly when taking into account thermal heat conduction. Because of this, it would be beneficial to compare the differences in analyses. Finally, topology optimization could be used to determine the best shape of the pressure vessel for a specific material. According to the results of this project, steel 316L with a 2.4 radius yielded the lowest maximum strain values in the lower corner regions. However, due to its physical properties, steel 316L may not be suitable for all applications as previously mentioned, particularly for the radioisotope power system. Therefore, the best setup choice would probably be the tantalum 10 tungsten with a radius of 2.4, due to its ability to withstand high temperatures. Thank you for watching.